Okay, in the last two classes, we looked at matter effects. In case 1, we took the matter density constant. Then the problem was quite simple. And case 2, matter density varies slowly such that so as long as the neutrino is in matter, the variation is slow enough that the adiabatic approximation holds throughout, and using that approximation I derived the solar neutrino survival probability, and also discussed that the data indicates that the solar delta m square has to be positive. Otherwise, if the solar delta m square is negative, then that could predict a different energy dependence of this survival probability, and the observed energy dependence is consistent only with positive delta m square. Actually, if you look up the literature of solar neutrinos, you find there is a third case which people have solved, but it turns out that the present solar neutrino data makes that third case irrelevant. I will briefly mention it. The third case involves a situation where in the last class I discussed this concept of resonance, where the delta m square is minimized and the mixing angle is maximized. So delta m square is minimized means the two masses are as close as they can be. And if you look at this adiabaticity condition, the most likely place where it will be not valid is at resonance. So we make the assumption that in the narrow region where the resonance condition is satisfied, adiabatic condition doesn't hold, but everywhere else it holds. That was the assumption people made. And non-adiabaticity means, adiabatic approximation means the heavier mass eigenstate remains heavier mass eigenstate, and the lighter mass eigenstate remains lighter mass eigenstate throughout. If you include non-adiabatic effects, then in the resonance region there is a chance that part of the heavier eigenstate, the word used is jumps into the lighter eigenstate, and of course by conservation of probability the same amount of lighter eigenstate jumps into heavier eigenstate. This problem actually was solved by Landau and Zener of the Zener diode fame in 1930s in the context of atomic physics, but the whole mathematical apparatus one can borrow, apply it to neutrinos and calculate this Landau-Zener jump probability. And when people felt that the solar mixing angle is very small, in such a situation, this Landau-Zener jump probability played an important role in providing a solution to the solar neutrino problem. But later data showed that the solar mixing angle is large, and one can show based on the adiabatic the condition for adiabatic evolution that if the mixing angle is about 20 degrees, adiabatic condition will always be satisfied. So if you see the references, this discussion, you will see this discussion, but it is not relevant in the present situation, at least not for solar and atmospheric neutrinos. Maybe there are some other situations where this may be relevant, but I will not explicitly discuss this. Instead, I will consider a fourth case where there is a sudden change in density. Then how does the probability change? Especially for atmospheric neutrinos, this is quite relevant because the picture of Earth we have is, it is roughly a sphere of radius 6,500 kilometers. But based on seismology and this one, picture we have is that there is a core with a radius of about 3,000 kilometers. And the density in the core is about 11 grams per cc, whereas this part is called mantle, where the density is about 5 grams per cc. And in fact, a very detailed model of Earth looks at it as 26 concentric spheres. But at a crude level, we can consider it to be two densities. Core with a density of 11 grams per cc and mantle with a density of 5 grams per cc. And let us say my experiment is here. Then you find that most of the phase space, most of the solid angle, the tracks are only through the mantle. Because see, I have to, so a track which sort of is tangential to the core is fully through the mantle, and any zenith angle in this range will be fully in the mantle. And what is this maximal angle? And from geometry you can see that it is 30 degrees. So for the solid angle actually goes as d cos theta. So d cos theta in the range 1 to 0, only 1 to 0.85 or 0.86 only those tracks go through the core. And cos theta from 0.86 to 0, those tracks they go only through the mantle. So one of the aims of future atmospheric neutrino experiments is to see this so-called core effect. Okay. The zenith angle that you are dealing with is only some 15% of the available. But especially for an experiment like ENO, where the vertical tracks are better reconstructed, whereas if the track is horizontal, the ability to reconstruct is quite poor. So the ability to see the core effect is quite pronounced for INO, and the geophysical models, of course, are quite sure that there is a core, but you want to see the effect of this core through some other means also, and this is one of the motivations for INO, that is to see the effect of the so-called neutrinos passing through the core. So then you would say, okay, the neutrino is produced here, traveling through atmosphere, it travels only 10 kilometers, we neglect that. It travels about 3000 kilometers in mantle, another 6000 kilometers in core, and another 3000 kilometers in mantle again. So I have to take this travel separately, this travel separately, and this travel separately. But also, whenever I'm going from mantle to core and then core to mantle, I have to sort of take into account the fact that the density is changing suddenly. So question is how to do that. That is actually quite simple to do, and in particular in quantum mechanics, in time dependent quantum mechanics, we have this concept called sudden approximation, and that is what we use. So let us say that I have two mass eigenstates, nu1 mantle and nu2 mantle. These are related to nu e and nu mu through the mixing angle in the mantle. So these are cos theta mantle minus sin theta mantle, sin theta mantle, cos theta mantle times mu e and mu. But similarly, we also have two other mass eigenstates, nu1 core and nu2 core, which is cos theta core minus sin theta core, sin theta core, cos theta core times mu e and mu. So let us, for example, assume that I have neutrino at time t. Which is passing through the mantle and has reached the mantle core boundary. Such a neutrino I will write as A1m, which in general is a function of t, times nu1 mantle plus A2m, which also is a function of t, times nu2 mantle. nu1 mantle and nu2 mantle form the propagation eigenstates in mantle. So, in that basis, I write my neutrino as a linear combination of the two. Now, so I have here mantle and core, and the neutrino just crosses over. It goes, let's say, from 1 millimeter below to 1 millimeter above. Then how do I look at this? So what I realize is nu e and nu mu, they also form a basis for my neutrino state. And nu e and nu mu, they don't care about whether the matter density is that of mantle or whether the matter density is that of core. So, I don't have to worry about change of the state when I go from here to here. So, what I will do is I will write this as a linear combination of nu e and nu mu. So I have A1m of t times cos theta mantle, and nu2 is A2m of t times sin theta mantle times nu e plus minus A1m of t sin theta mantle plus A2m of t cos theta mantle times mu. So this is the state at the lower edge of the boundary, and now I consider the state at the upper edge of the boundary. So at a time delta t later. So at a time delta t later, the density has suddenly changed. So the propagation, what we call propagation eigenstates, have changed. But the neutrino state cannot suddenly change. So this is the important point, and this, like, for example, if you are going in a bus and the driver suddenly slams on the brake, you are thrown forward. Why is that? Because you are in a state of motion with some velocity, and the fact that your environment suddenly changed does not, your state of motion doesn't change as fast as your environment. So you try to continue to move. with that same speed, and relative to the bus you are thrown forward. In a somewhat vague sense here, going from here to here, environment has changed, but the neutrino state is still this. For delta t change of or delta x change of planes, the amount of evolution the neutrino state will have is so small, I neglect it. So, the state which is there at t plus delta t is essentially the state that was there at t. But, and of course, I have written it in terms of nu e and nu mu. Something times nu e plus something times nu mu. But the new environment, the propagation states are nu1c and nu2c. So, in order to consider further time evolution of this state, I should rewrite this in terms of nu1c and nu2c. And I do that. If I do that, I have, okay, I'll call it some A and B just to simplify my notation. So now I write nu e and nu mu in terms of nu1c and nu2c, and when I do that, I get this to be a cos theta c minus b sin theta c times nu1c plus a sin theta c plus b cos theta c times nu2c. And now I substitute for this a and b. So in a, you see that I have a1m t times cos theta m plus a2m times sin theta m. This whole thing is multiplied by cos theta c minus, and there is a minus sign there also, minus a1m sin theta m plus a2m cos theta m sin theta c. This whole thing times nu1c plus something times nu2c. Now, if I gather together the terms, so I gather together the A1 terms. I have cos theta m cos theta c plus sin theta m sin theta c, which is cos of okay, I should probably write m minus c. And for A2 m, this is sine of theta m minus theta c. Because I have sine theta m cos theta c minus cos theta m sine theta c, which is sine of theta m minus theta c. And if you work it out for this dot 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 I have put here, you will find that that is plus minus a1m, or let me, yeah, okay, minus a1m sine theta m minus theta c plus a2m cos theta m minus theta c times into c. And this I will write as a1c of t mu 1c plus a2c of t mu 2c. So what is the transformation property? I find that a1c of t a2c of t is equal to cos of theta m minus theta c sine of theta m minus theta c minus sine of theta m minus theta c cos of theta m minus theta c times a1m of t a2m. Yeah.
You're looking at just that time t or just at that particular
at that instant, at the crossover instant. Otherwise, there will be extra phases involved. So this relation holds at the crossover point. So and once I have a1 of c, then within core that will propagate independently, and A2 of C within core that will evolve independently. Yeah. So if you want to talk about probability of the lower mass eigens, this is the amplitude for the neutrino to be in the lower mass eigenstate of mantle. And if you want to ask, okay, what is the probability of the lower mass eigenstate in mantle to be in the lower mass eigenstate of the core also, then that is cos square of theta m minus theta c.
That question is not important.
Yeah, I mean, usually we do not bother about that question, because what we are interested in is the final probability for a neutrino produced as muon neutrino on the other side of the earth. What is the final probability that it is there, it appears as a muon neutrino in my detector. But I mean, so basically wherever there is a sudden change in density, we use these transfer matrices to go from one density to another to get the corresponding amplitudes in the new density, and then do the time evolution. Okay, till now we have worked in effective two-flavor mixing approximation. Now let us consider and again, if you see literature, you will actually see people trying to solve solar neutrino problem with matter effects in three flavor oscillations. But again, the present data says we don't have to do that. So we limit ourselves to matter effects in three flavor mixing that are relevant for long baseline oscillations and also to atmospheric neutrino oscillations. Now, the evolution equation, the vacuum evolution equation is I ddt nu1 nu2 nu3 is equal to m1 squared by 2e times I plus 0 0 0 0 delta 2 1 0 0 0. In the two flavor case, we have written it so that we modded out m1 square plus m2 square by 4e. But here we mod out only m1 square by 2e. So here I have a delta 2 1 m2 square minus m1 square, and here I have a delta 3 1. And I want to add the matter potential, but matter potential I can add in the flavor basis, not in the mass eigen basis, and I have the flavor basis is u times the mass eigen basis. So I have to do the ulta, means mu m is u dagger mu alpha. So I have I ddt of, this is a constant matrix, so I can pull it out of the differentiation and multiply from the right by u. So I get mu e mu 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 tau is equal to, and something proportional to identity does not affect my oscillations, so I forget about it. 1 over 2e times u 0 0 0 0 delta 2 1 0 0 0 delta 3 1 u dagger mu e mu 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 tau. This is the vacuum evolution equation in flavor space. Now I add the matter term. So I get I I'll put 1 over 2e out. So first I have this. Then I have the matter potential is the 1 term, but I have pulled out a 2e, so I have to multiply it, and 2e times v I am writing as that Wolfenstein term A. Now if I multiply out these three matrices, I get some complicated matrix to which I add this A matrix, I get some other matrix, and I diagonalize this 3 by 3 matrix to get 3 mass eigenstates, and then I have the corresponding mixing matrix. And so numerically I know how to do this problem. This is a diagonal matrix and this is a unitary matrix, so this will be a Hermitian matrix. Addition of this also makes it a Hermitian matrix, so I am guaranteed to have real eigenvalues and I am guaranteed to get orthogonal eigenvectors, and in principle I can close my eyes and just do the calculation numerically. However, we want to sort of gain some insight into the problem. So instead of doing the problem numerically, we would like to do it algebraically. So to do it algebraically, we first use a simplification. I mentioned earlier that at long baseline experiments, the important mass square difference is delta 3,1, and in fact, the Minos experiment, which measured delta 3,1, did so in the approximation of setting delta 2,1 equal to 0. So, let us set delta 2,1 equal to 0 to begin with. If I do that, then let us look at this U. U is R23, U13, R12. I hope you understand the notation. This is mixing only with the second, third rows and columns, first and third rows and columns, first and second rows and columns. And if I set delta 2,1 equal to 0, this matrix is 0, 0, 0, 0, 0, 0, delta 3,1. And R12 transpose, U13 dagger, R23 transpose. And you note that this R12 transpose acting on this leaves it just the way it is, because this is block diagonal and the 2 by 2 block consists of all zeros. So, and there is a phase involved in this U13, and one can demonstrate that that phase also will not matter. So that is the first thing I do. And second thing I do is I take R23 transpose and act it on mu e, mu tau, or and I get mu e, mu tilde, mu tau tilde, where this mu tilde, mu tau tilde are some arbitrary states I have defined just for my convenience. Now, you see that I can write my by the way, this R23, I bring it to left side so that this R23 transpose acts on this. And so with that, you find that I can write my evolution equation as I ddt mu e mu tilde mu tau tilde times 1 over 2e times U13 0 0 0 0 0 0 0 0 delta 31 U13 dagger plus A 0 0 0 0 0 0 0 0 times mu e mu tilde mu tau tilde. And you note that I can think of this also being block diagonal, in the sense I consider the first two rows and rather first row, third row, first column, third column, that I'll think of it as a block, and then this one is a separate block. The important thing is this matrix and this matrix, they both have second row, second column consisting of zeros, and this U13 dagger, they will not touch the second row, second column. So I can that is one way of putting it, but now actually the problem has simplified. Here the second row, second column sort of decouples from the whole, from the other two, and I work out this matrix, add this matrix to it, and then I have essentially a 2 by 2 diagonalization to be done, which I can do algebraically and get the eigenvalues, the matter modified value of theta 13 and the matter modified value of delta 31, and using them I calculate my survival and oscillation probabilities. It's a bit of algebra, but one can do that. So if you do that, so now the problem reduces to two flavor oscillations, but mind you, the two flavor oscillations are between UE and this funny state mu tau tilde that I have defined, and the oscillations are driven by the matter modified theta 13 and matter modified delta 31, and I can calculate all the probabilities. By the way, I have written U13 dagger here as if there are phases in these matrices, but in the approximation in which I am working, you find that these phases will actually cancel. So my answer does not depend on the phase. And if you work out, you will find that P nu E is the expression for P nu mu to nu mu, it turns out is reasonably complicated. I won't explicitly write it down, but given that it's a two-flavor oscillation problem, in principle, one can derive that. And what are the expressions for these matter modified?
This assumption, would it become exactly two-flavor oscillations?
No, it's not exactly two-flavor oscillations. I shouldn't have said that. But as far as the dealing with the matter effects is concerned, it is effective two flavors. But it's not a two-flavor oscillation. There is nu mu to nu tau probability, nu e to nu tau, all those are there. Yeah, it's that was not a correct statement I made. It is indeed a three-flavor oscillation problem, but matter effects can be handled as if it's a two-flavor case. So the expressions for matter modified theta 1,3 and matter modified delta 3,1, they look exactly like what we have seen in the two-flavor oscillation case. And it looks as if now it's a simple matter to measure the sign of delta 3,1. Because if delta 3,1 is positive, then as energy increases, A increases. So there is chance of better and better cancellation here, and theta 1,3 matter goes up. Whereas if delta 3,1 is negative, then there is no chance of cancellation. This keeps becoming larger, which means the denominator is larger. So theta 1,3 matter goes down. Well, to start with, it was a problem because theta 1,3 was not known. It was measured only in 2012. And also it is known that theta 1,3 is small. It's only about 8 degrees or so. But once theta 1,3 is measured, and it is measured in an experiment where matter effects play no role. It's measured in those short baseline reactor neutrinos. And for reactor neutrinos passing through Earth, you can completely neglect the matter effects. The energy is only some 5 MeV or so. So then you just measure this nu mu to nu e oscillation probability. See whether it is more than what you expect or less than what you expect, and based on which you determine delta 3,1, sign of delta 3,1. Seems like something very nice and straightforward. However, we should remember we did this derivation in the approximation of setting delta 2,1 equal to 0. And we know delta 2,1 is not equal to 0. So, what we have to do before we make this statement about sign of delta 3,1 is we have to rederive the probability including delta to 1. And when we include delta to 1, in the approximation of neglecting delta to 1, the phase in U13 is disappearing. But if I include delta to 1, the term which is proportional to delta to 1 will include that phase. And I have no idea what that phase is. So, you have this two unknowns. I don't know what the phase is. I don't know what the sign of delta 31 is. And I need to solve both these problems simultaneously. So, which of course makes life more complicated. So, I will stop here for now because I don't want to start the discussion. That will take time. I will use the entire next class to discuss that. So, what we will do is we will treat the delta to 1 term as a perturbation to this and develop an analytical formula. I won't do the derivation. Derivation conceptually is straightforward but algebraically quite tedious. If you try to do the algebra, it will probably take you 2 or 3 days. But conceptually, it is straightforward perturbation theory. If you do that, then there is a correction, there is an additional term. This is what I have derived as nu mu to nu e oscillation probability in the limit delta to 1 equal to 0. But there will be a correction which is proportional to delta to 1. And that term depends on this total unknown delta Cp. So, I have this probability which depends on two unknowns. So, the effect of one unknown in principle can be cancelled by the effect of the other unknown. So, we have what is called hierarchy delta Cp degeneracy in the problem. And this is what makes life very, very complicated in looking at the nu mu to nu e oscillations in long baseline neutrino experiments. So, this point I will discuss in the next class.